managed all the logistics and for this. So she'll deserve a round of applause for putting this together, because it's been a ton of work. What's Greg doing? So on the agenda, just a little background. A while back, I had not been at a previous tech day that the club, W0TLM, the Trial Lakes Monument Club, had done previously. But I had more recently, Bob Whitty and I put together, put together a survey, a real detailed survey. We got close to 100 responses from the people that are on the W0TLM mailing list. And one of the things that occurred is there were so many comments about wanting to talk about antennas as a subject that people wanted to learn about. So we thought, let's put together a tech day and address that, because if you tried to do that at our monthly presentations, that would be a pretty long, drawn-out process. So here we are today, and the idea is that, face it, you guys are in a technical hobby. We're going to cover a little bit of that real technical stuff. Don't get too worried. There won't be any math involved, and there won't be a test at the end of it, unless you're planning to upgrade, on which you'll learn something that will help you on the tests if you do plan an upgrade. And you'll see some references in some cases where this is related directly to a question on an extra class exam. I didn't go back and look at the general class, but I know that there'll be a few of those. But we're going to cover a few of those, and that got left to me this morning. Pointer, is this? Be sure to turn it on. Okay. Greg, I'm going to leave this technical aspect to you, and if you can figure it out in your time. Okay. So I'm going to warn you. Or let me ask the question first. How many of you hear the term Maxwell's equations and your head just kind of explodes, or your eyes glaze over, or raise your hand if you've never heard of Maxwell's equations?
John Maxwell, leadership.
No, we're talking about James Clerk Maxwell, the Scotsman from back in the 1800s. We'll talk about him just a little bit. So don't fear. It works. So, outline a little bit about electromagnetic fields. Without electromagnetic fields, you would not have the ability to communicate over the air. And that pretty much applies to cell phones, Wi-Fi, Bluetooth, and the amateur radio bands, TV, radio. We're going to talk about antennas. We're here today to talk about antennas. I'm not going to talk very much about specific antennas. That comes later in the day, where you're going to get some practical presentations on how they work, how they're set up, and nuances related to the different types of antennas that are going to be dependent on your needs. And I'm going to cover terminology, because a lot of the terminology is actually related to the physics, the physical properties of these antennas. Then we're going to talk about transmission lines. How do you get a signal to the antenna so that it does radiate, or how do you get it back from that antenna so that you can hear a signal? And a few other items, SWR, balance, and I don't know how long this presentation is going to take. I put a bunch of slides together, and I got 2 hours. I don't think it's going to take quite that long, but there should be plenty of time for questions. So, electromagnetic fields. I will admit, I was trained as an electrical engineer. I'm going to show you in just the next few slides pretty much everything that I remember from a full year of a 400 level engineering class in 3 slides or so. So it's going to be pretty condensed. Whoops. Greg, help me, I pushed a little bit, thank you. So, when I was about 12 years old, I was fascinated with the fact that I could turn a knob on an old radio and hear different radio stations, and it was magic. A couple of years later, I grew up in a little town out in the sticks in west central Minnesota. There was one ham in the town where I went to high school, population of about 350 people. And there wasn't a lot of help, but he gave me a couple of books. I have a copy of the 1957 ARRL handbook, and that's pretty fascinating. And it's funny though, the physics hasn't changed since then, and it hadn't changed since ever. And they cover a good bit of that stuff. So, the magic, don't be intimidated. We're going to talk about the physics of it, but like I said, that part's going to go quick. There are two simple concepts that, oh shoot, it wasn't even high school, probably it was in middle school. You might have made an electromagnet, or you might have seen how an electric generator works. A generator, we're turning an armature, we're moving a wire through a magnetic field, and oh my, we generate electricity. That's how all of the electric generators work today. We'll get to how that applies to radio signals in a second. The other item is, current in a wire creates a magnetic field. Do you ever wind wire around a bolt or a nail and pick up paper clips with it? Kind of like that. So, electric fields and magnetic fields. Oh, wait, we're talking about electromagnetic fields. These two principles apply. They are the underlying properties. So what's an electromagnetic field? It's a combination of that electric field created by an electric charge, voltage, and a magnetic field created by charged particles, electrons that are moving through it. That's a wire, that's an antenna, and that's the principle of creating a signal that will go from point A to point B. Actually, it goes from point A to everywhere, as we'll see here in a few minutes. Maxwell's equations form the foundation of the classical electromagnetic, classical optics, electric circuits, providing a mathematical model for these. Here's where your head blows up. It'll be brief. These are Maxwell's equations. I'll call them simple equations because when you start putting them together and do the math, that's what took the full year of that classic college. But if you notice, too many buttons. If you notice, these two equations, Faraday's law, a varying magnetic field creates an electric field. We just saw that in a generator. Ampere's law, current in a conductor creates a magnetic field. Again, this is where it started to get all of the science related to propagation of an electric signal. Last really sciencey chart here, I think. If you notice, this E represents the electric field, H represents a magnetic field. They are at 90 degrees to each other. This is significant. We'll get into a bunch of that later. But the combination of those two vectors creates a new vector that points in a specific direction. It's called the pointing vector. And that is how power is transferred through space. And it's because of an electric field. Notice the sine wave. The frequency is important here. This frequency, whether it be 630 kilohertz at the bottom end of the AM radio band, or light, or gamma rays at the really high end of the electromagnetic fields that are generated. So, as these change in frequency, can't really read it here. It says direction. That's how your radio signal is propagated. referred to in energy flux. We're measuring that with test equipment, but you're also measuring it with your receiver. How many of you have, with your handy-talkie, have been in a fringe area and all of a sudden it goes from clear signal to you've lost the full quieting on your FM radio? Well, you're in an area where that electric field has diminished. What we're trying to do to improve signal, improve connectivity, is increase how that signal works. And that's where the practical stuff of antennas come in. I'll come back to this a little bit later here. So, this is practical stuff now. The wavelength, going back here, the wavelength is from a maximum to the next maximum, or from a minimum to the next minimum on these sine waves. That is represented by lambda, which is the Greek symbol that physics and engineers have used forever to represent what is that wavelength. And it is c in the formula, the speed of light in a vacuum, and this is an important thing that we'll learn about a little bit later, divided by the frequency. Or it would be the wave speed, because RF signals don't necessarily move at the speed of light through a medium like a wire, a coaxial cable, divided by the frequency again. So you may remember the speed of light is, I don't think anybody remembers that number, but we round it to 3 times 10 to the 8th, or 300 million meters per second, 300,000 kilometers per second. So, just for grids, let's calculate the wavelength of 14.275 megahertz. So we're in the, we know that as being in the 20 meter band. Well, we can confirm that. 3 times 10 to the 8th divided by, in engineering notation, that would be 14.275 megahertz, or 1.4 times 10 to the 7th, is 21.01 meters. Something different about engineers versus physicists. Physicists deal with the exact, and ham radio operators, or engineers in general, deal with that's good enough. That's really the biggest difference between a physicist and an engineer in a specific discipline. So we'll revisit this transmission lines, because the wave speed, as I mentioned, in the coax cable is slower than the speed of light. Any questions? Anybody feel like taking a physics exam? All right. Hopefully now, head explosion should be completed. Oh, sorry about that. We got to talk briefly about reactants. Whenever you put up an antenna, there is a situation where you want to match the antenna to the transmission line, to the output impedance of a transmitter. It's a practical thing that we do. And show of hands, how many people here are only doing VHF or UHF with an HT, or maybe a mobile station or base station? So quite a few hands. I'm encouraging you to upgrade and experience HF, because it can be very rewarding if you're interested in seeing who you can communicate with. I don't want to say talk to, because it's hard to consider CW Morse code as talking to somebody. Greg exception here, almost exclusively is on CW if he's in the HF bands. But this becomes a lot more complicated. At VHF, there's a lot of nuances, but really, screw in the rubber duck or a whip to your HT. You're not really worrying about this, but understand that the people who design those antennas, if they were any good, were paying attention to this. So, terms that you're going to hear. Z is impedance, which is comprised of a resistance plus or minus a reactance. And all of this is expressed in ohms, and there's a couple of ways to do that. And this is important because later on, we're going to talk a little bit about impedance matching. So, reactance J is the imaginary component of impedance. And this is a mathematical concept. It's not an imaginary signal. It's actually happening, but what it's really referring to is that there are phase shifts involved. J represents a positive J represents an inductive reactance, which is this area pointing up. We go 90 degrees further, we're at a -1, a real number. We go a little bit further, we're at a negative J, which represents a capacitive reactance. I think these are on the exam questions that are general for certain. And, that's all just extra, not in general? Okay. Sorry, I'm encouraging you to upgrade at some point to general and remember this sort. But the formula for an inductant is 2 pi f. You remember if you ever took trigonometry, going around this one time is 2 pi radians. F, frequency, how many times do you go around that circle? How many times is that signal shifting at 14.275 megahertz? Well, 14,275 times in a second. That's the representation. Capacitive reactance is 1 over J 2 pi F. Here, J. This should have been a C right there. Negative J over divided by 2 pi f C, because moving the J from the denominator to the numerator results in a negative J, negative shift. Voltage leads current in an inductor. That's a principle that applies to Colorado Springs Utilities or whoever is providing power out here in the Black Forest, because it relates to a power factor. Things go a little bit wonky when your current is not in phase with the voltage, and that's why motors have big starting capacitors in many cases, is to not just provide a voltage to start a motor turning, but also to adjust the phase shift of that signal. Voltage lags current in a capacitor. You're charging up the capacitor. Think about it as a modification of a battery. It's storing energy, but it takes time to store that energy in the capacitor, and that's why it lags. But here's where we start to get, you don't need to remember this, but this is some of the principles again of these changing magnetic and electric fields that are part of that signal propagating. Antenna resonance. You hear all the time, and you're going to hear a number of times this afternoon, about a resonant antenna or a non-resonant antenna. Question: does an antenna need to be resonant to radiate? Anybody think that it does? Good, because it doesn't. What it means is that component in the impedance is 0. Well, that doesn't translate to propagation. What it translates to is impedance matching that we'll talk a little bit about later on. So no, resonant antenna does not even necessarily have a low SWR. We'll talk more about SWR. But we frequently hear, and I've seen these on YouTube videos, is somebody talking about, we've got to get it resonant to lower your SWR. No. I mean, they sometimes can go hand in hand, but that's not what people need to be thinking about. That antenna impedance is frequently expressed, and how many of you here have an antenna analyzer that will measure a lot of hands? So when you plug it in, turn it to the frequency that you're interested in, you will generally see a resistance with a plus or minus J. Well, on a chart, here's the resistance. This on the positive imaginary is the inductive reactance. These numbers, I found a slide that represented this easier. It doesn't represent 45 plus J15. This would be 6 plus J4 on this antenna. But that is also has a magnitude here and an angle, and it's just the difference between expressing the same number in rectangular coordinates r plus jx, or in this case, it's z with an angle of some degree. They're identical things. It's really important because it is a royal pain to multiply two numbers together, which you sometimes have to do if they're in rectangular coordinates. It'll take you, thank God for computers. I had to do this with a slide rule and graph paper when I was doing it. But you can simply add or subtract in rectangular. You can multiply and divide very easily. Let's talk a little bit about radiation efficiency. By the way, I'm just running through terminology that you will hear or see when you're looking at antennas that you're trying to do. Don't feel like you have to remember them, but if you just got a hint of the concept, these are not calculations that you have to do, but it's something to strive for. As it states, radiation efficiency, how well are you putting a signal out into space? That resistance is characterized by the radiation resistance and the loss resistance. As might be intuitive from looking at that, if you have a lot of losses, you're not going to be as efficient, and that's really what's happening. The losses represent power that gets dissipated before it gets propagated. It sometimes shows up as heat. Well, it will show up as heat. It has to go someplace. So that is resistance in the transmission line. It might be imperfections in impedance matching networks. A balun that is installed, baluns will heat up because of energy loss in that. That energy loss means the signal that's being propagated is not as high as you would like it to be. We're going to hear that. We're going to hear that theme. We're trying to maximize. And when we say that, when we say that it radiates efficiently, it also receives. It's kind of it's just the reverse process, just at a lot lower power. We're transmitting it certainly at higher power than we're receiving at, or you'd be letting the smoke out of your receiver if it were the other way around. This is moving along fairly quickly. Antenna gain. The antenna gain is expressed in dBs, decibels, a logarithmic factor, so that instead of seeing charts that have this big kind of curve, mathematicians, physicists, engineers put it in a logarithmic scale, which is a whole lot easier to look at. This represents the radiation pattern of an idealized antenna called an isotropic antenna. It means a single point. That single point will radiate exactly the same in every direction. It doesn't exist, but it's a good reference point to say, if it did, this is how much better an antenna would be. And then you see it expressed as dBi. The I standing for isotropic. Let's see. One of the questions on the extra exam, that it's a theoretical omnidirectional antenna. Gain expressed in dBi. That almost verbatim is the answer to one of the questions. The measured power density, the watts on that surface, would be identical at any place around that. So, but of course, people will do things to throw you. Sometimes that antenna is represented in gain in dBd. dBd is reference to an idealized dipole, half-wave dipole antenna, where here's the antenna in the middle, and the propagation pattern goes out broadside to it. So the maximum propagation off of a dipole is going to be, if this is east-west, it will be north-south. Again, ideal dipoles, it's going to depend on how high it is, how many wavelengths above the ground, get certain reflections off the ground. Idealized, but it's a good reference point. The interesting thing is, mathematically, they figured out that this reference antenna is 2.15 dBi, meaning the gain is 2.15 or 2.2 decibels greater than an isotropic. So when you're looking at what's the gain of the antenna and comparing, it's got to be apples to apples. If you're looking at a dBi number to another, from one to another, and the other is the dBd, there will be a 2.15 decibel difference. Yeah.
Is that always in the maximum direction? Maximum gain?
Yes, because idealized coming off the ends of this, 0. So always measured when they're giving the gain of the antenna, it would be in the maximum direction. Right?
And the idealized dipole is in free space. It's not reference to ground.
Well, yes. And you can.
So it also doesn't exist.
It doesn't exist. No, there's also always going to be some factor that's going to adjust these. But you need a reference point, and that's the reference point that they use. Polarization. This, hopefully, when I finish this section, we're going to be able to give you a demonstration. It isn't going to work great inside this room. We'll take it outside, maybe at lunchtime or later on when we're doing some demos. But we want to show you, and I brought this chart back, the E and H fields. When an antenna is expressed as being polarized, they had to pick a reference way, and what they're doing is they're talking about the orientation of the electric field in this pattern. So, M or magnetic, H is a symbol that's used, though these are interchangeable in this reference point. The electric field is pointing straight up. This is the signal from a vertically polarized antenna. It's always the electric field, the voltage field, that references the polarization. That's convention. A dipole, which would be horizontal to the ground, horizontally polarized. So what that means is that if you just rotated this 90 degrees, now the E field is on the x-axis, the y-axis pointing up would be the magnetic field. Sometimes an antenna can be circular. Well, let me back up a second. Ideally, again, we're dealing with ideal things. If you have a vertically polarized transmitter, and I'm trying to receive it with a horizontally polarized dipole or a directional antenna, like a Yagi, multiple elements, all in one polarization. as I turn that, ideally, when you go opposite in polarization, that signal would drop to 0. Doesn't happen, but hopefully we're going to be able to show you that we can rotate that antenna on its axis, and you can hear the signal dropping as it gets out of orientation. Sometimes an antenna can or needs to be circularly polarized. Satellite operations, for one. These little cube sets that are up that are FM transponders or repeaters, transponder I think would be a better terminology for it, are tumbling. They're rotating. Well, there's a little vertical antenna that's sticking out of that box, and its orientation is changing as that satellite tumbles. And if you've ever listened to a satellite signal on a polarized antenna, you will hear the signal fading, coming stronger, fading, coming stronger. A circularly polarized antenna, what you need is two orientations of something that will be picking up the electric field on that. If you've ever seen satellite antenna designs, you sometimes see a number of elements on one axis, and then there'll be a second element that's at 90-degree angle, perpendicular to the other element. Well, those aren't identical elements because they are phase shifted by 90 degrees. So what happens is that as in this orientation, as the electric field hits a max, there's another electric field on the other elements that are going off in this direction, and when it's shifted 90 degrees, the other one is at 0 in the phase. So what happens is, as one signal is going down, the other element is starting to come up, so that when on one direction you're not picking up any electric field, but it's maximum at the other orientation. And this just changed, but that only happens because those two elements that are perpendicular and almost in the identical space are 90 degrees out of phase. They're 90 degrees out of phase, the receiving is 90 degrees, so that the signal remains constant on both of those.
Sorry.
We have an uninvited guest. Yes?
So how is that phase shift achieved? Is it by placement of the elements or efficiency?
It's done, and that's a great question, because I've got, we're going to talk about that explicitly coming up, how that's done. But it's a phase shift in the feed line. So you're feeding one element, and there's actually a quarter wave at the frequency, a feed line that is a quarter wavelength long that is creating that 90-degree phase shift. And I can show you how that works on a chart that's coming up. And another extra exam question. So let's talk about antenna directivity. And this applies any frequency. I'll show you one. Sorry, I gotta go off camera here for a second. This is a 2-element Yankee antenna for 2 meters. So this element in the back here is a half-wave dipole. So from tip to tip should be half a wavelength. If this is 2 meters, that's about a meter. Yeah, that's about a half a wavelength. And now we have a directed element. If it were a 3-element beam, these would be spaced out. I don't know the math to figure out exactly what the spacing is on this. But if we had a 3-element, we would have a reflector back here. The reflector would be a little bit longer than the driven element. The directed element would be a little bit shorter. And what results from that is we're putting a lot more signal out in one direction than we are off the back. And oh, by the way, the side lobes are suppressed. Now this doesn't represent a 2 or 3 element Yankee. This is probably a much higher frequency, and this is probably a whole bunch of elements that are providing this, because that's a really high gain. Doable on microwave frequencies. Pretty hard on HF to do that. So, a couple of things to put this down. By the way, that'll be part of the demo here. Front to back ratio equals the amount of power in the desired direction. Power meaning the power that's transferred out of the antenna divided by the power directed in the opposite direction. Why is it divided by? Well, because we're talking about decibels here. Logarithmic math is that when you divide two numbers, you're actually subtracting the logarithm of those numbers. So when we calculate what the difference is, we look at the gain out here. And just for grins, let's say that that's a 10 dB gain, or a 10 dB level, and then this inner ring is 5 dB. The front to back ratio of that would be 5 dB. We're subtracting the logarithms. So we don't have to, but it's actually the power forward direction divided by the power in the off the back side of this. The front side ratio equals the amount of power in the desired location divided by the power off the side lobe. Well, we may be 10 or 20 dB down off the sides of this directional antenna. So, why would you do that? We'll get into more detail, but I'm able to pivot this around. I can direct it at the location where the desired received signal is originating from. And the other advantage is if we're in a noisy environment, the signals coming from other directions are going to be significantly suppressed to make the desired signal stand out. So this directivity, a dipole is a directional antenna of sorts, because you're operating primarily to 90 degrees from the direction that you string the wire. And then another term, beam width, is defined by the number of degrees between the point where the signal is down 3 dB from the main lobe. So that would be, here's our 10 dB. At this point would represent 7 dB of signal, and the width is the number of degrees. Notice we're at halfway, or a quarter of the way around is 90 degrees. So making a guess, this looks like it's about from this point to this point, 15 degrees. So that means that when we're talking power, 3 dB is the half power number. If I've got a signal, directed with that 10 dB gain, there's only 7 dB just by going off 7.5 degrees from that number. So directivity is a really, really important thing. If you have a directed antenna and you're not aimed, in many cases, if that's a weak signal and just a little bit above the noise floor, you won't hear the signal that's coming from just a few degrees off to the side. Yes,
I've seen some GHF antennas that have multiple directional elements. Here's the question. On the HF bands, a regular 3-element tri-beam, is a 4-element tri-beam any more efficient than the 3 being in the HF?
could everyone hear the question? Okay. The answer is, sorry, I'm smiling because this is where the terminology becomes more important. In terms of the efficiency of the antenna, it may not be more efficient as we define what efficiency was. The amount of power that is put out is really all of the power that's put out versus. So,
I'm more concerned with
no, I'm,
from the reflective to the point at where you want to point the signal.
so it won't make that antenna more efficient as we define what efficiency is, but it will, what if that fourth element,
Yeah.
presumed it's been designed appropriately and it has the right spacing and it's the right length. What that would do is make this come out here a little further, probably narrow this up, move this one, the front to back ratio would probably increase. So instead of using the word efficient, it would probably be more effective if it's pointed at that. I'm being a little pedantic here because this is where people get in trouble on a lot of random YouTube channels, is some of these terms sound like they make sense, but they're not exactly accurate. And so the antenna will be more effective because it's more direct, it has greater directivity.
And a follow-up on that one, is a quad construction more effective than a yank?
I'm gonna say that is a gigantic, it depends.
Okay.
Because in principle, they're doing the same thing. You've got, instead of a long horizontal, what you've done is you put those wires in a square, or it doesn't have to be a perfect square, but the answer is that it will provide directivity, it will provide gain in a particular direction, it will reduce reception or transmission off the sidewalk or to the rear. So they're really done the same way, and the reason you would choose one over the other frequently depends on how high can you get it in space involved. Because the quad antenna will have a smaller turning radius because you've got elements that are not stretched out horizontally. So, but in terms of being more efficient, without being able to measure the field strength of that antenna around, it's kind of hard to answer the question. But it would be more effective.
And more direction.
Yes, Chip, you had.
That's the whole point. In general, if things are properly engineered, the more elements you have, the more directive it is.
Yes.
It's a simple answer.
Yes.
How does the stacking
The answer is if you have enough tower to where you can stack directional antennas, you will get greater gain in that direction. Or, I mean, you could actually point them in different directions. If you didn't want the directivity, but you wanted more power that would be transmitted in multiple directions, you can do a number of different things in that manner. So the answer is, again, you generally would stack it to get more gain and more directivity. But you end up introducing a number of other factors. Now we're getting back into that engineering or the ham radio concept of good enough. It won't be perfect. You can't just say, well, I'm going to get twice as much if I do this. But if I get 1 3/4, you know what, that's good enough, kind of thing. So to really answer that question, we could probably spend a week or two on showing the math. Not going to do that. We got tools, and it's kind of good to see what other people have done with their towers.
And is this transmission or reception, or both?
Both. Both.
So a simplistic question is, I use a old TV antenna to collect the HD signals. It's got a bunch of elements, that's what you mean, right? The process.
Yes.
And if I am in a situation where I'm not able to really point exactly where I need to, if I took some of those elements off, would I possibly be able to get more reception?
So the TV antennas in the VHF range are typically not Yankee antennas.
Even though they look like it,
Well,
kind of.
they're log periodics, is what the reference is, because you get more of a V shape
Yeah.
from those, which has the effect of making the antenna more broadband.
Oh, okay, so it's already trying to do
So
that.
it's trying, and so that TV antenna wasn't designed to be broadband in the ham band, but it's close enough to where it's doing better probably because it's up in closer to free space than it is, and it's a much more efficient antenna than that little dot. In many cases, back to that original question of, does an antenna need to be resonant at the frequency it's being used at? Well, that antenna is nowhere close to resonant at the ham bands. But well, one of the jokes is, if with the right antenna tuner, you can load up a bicycle frame or a light bulb, and people have done experiments. We're not talking the exact science. I would not remove elements from that, because that was designed to be a wide bandwidth antenna. And the fact that it says, oh, it's designed for, what were the VHF frequencies? They were just below the 2 meter band, weren't they? Let's see. Yeah.
For TV, channel 13, you know.
Yeah, that's right. It was 75 meters roughly up to about 108, which is the start of
Up to 88 there.
up by that. Yep. So,
Tangent.
no, and actually, that's a great question, because notice that, we're talking about where it falls off. If you looked at the frequency, optimized frequency for that antenna, you would see a dip in the SWR of it at a certain frequency. Well, it's probably got a much higher SWR. So where you can run into difficulty is if the output or power amplifier that's driving the signal isn't matched properly, it may put out less power. So from a receiving standpoint, you wouldn't care. The transmitter might not like that. We're going to get into that when we talk about some impedance matching things. The answer is, if it works, keep using it.
Sure.
If your transmitter gets hot, maybe you ought to think about finding an antenna that is designed for that frequency.
It's just reception.
Any other? Yes.
I'm not clear yet about that. Is it still direction?
Yes. Oh, yeah, definitely so. I didn't cover any of that, but you can find charts for it. Yeah, and again, when you're looking at this, you're going to look at these terms: front to back ratio, front to side ratio, and the beam width. And the beam width on that is going to be, fairly important. And I can't tell you what it is in an antenna like that off the top of my head.
Well, that's why you have to point the antenna toward the transmitter to channel 13.
Exactly. Mitchell?
One of the things that's really interesting about those older television antennas, if you look at them, almost all of the elements are actually connected to driveline. So it's not a Yagi type antennas, they're not acting as reflectors. They're different tuned elements for the different channels because they're fairly widely different frequencies. So you can really think of it as just a bunch of stacked backwards.
Yes.
So to your point earlier, you could probably not change the performance of it by taking elements out. But you need to make sure what frequency those elements were really for, and that's what makes the log periodics really broadbanded. is- So we're doing pretty good here. Okay, here's something that is going to apply later on in Greg's presentation about safety. But if you have a 100-watt output from your HF transmitter, or let's say 50 watts from a VHF mobile rig, or 5 watts from your HT, that is the output power of the transmitter, the power amplifier, or whatever the last stage of amplification you have in your transmitting system. The ERP is the actual power radiated from the antenna, taking into account all the gains and losses in the entire system. So, if you have, we'll take a really simplified case. Let's assume there is no loss in the feed line or the coax from the transmitter to the transmitting antenna. And like that directional antenna we saw just a moment ago, it has a gain of, let's make it easy math, 10 dB. So I'm transmitting 5 watts out of my HT. I've got a 10 dB gain antenna. The affected radiated power in the direction that antenna is pointing, 10 dB gain represents a 10 times power gain. You have an affected radiated power of 50 watts. If you have a 100-watt amplifier and a 10 dB gain in your system, you have a 1,000 watt, a kilowatt of affected radiated power. How that works, let me back to this. There is power in the system, and there's an efficiency factor. There are losses, but the efficiency factor says this is how much power is being transmitted. Well, if it were an isopole antenna, all of that power would be radiated in every direction, but now we're directing that power. So it's like concentrating that 100 watts into a narrow beam, which takes the power from the other directions and boosts it in the direction of interest. That's how you gain distance. That's how you raise your signal above the noise floor. That's how you get full quieting in a repeater or in an FM signal where you're hearing the signal and all of a sudden it pops up. That's because you've raised the radiated power in that direction and somebody is fully quieting that system. So, again, important question. Transmitter output power minus the feed line and matching system losses and the antenna gain. One thing we haven't talked about yet, here's a dipole radiation pattern. Notice it changes. This 0.25 wavelength is the height above the ground. So if this were a 20-meter dipole, 14 megahertz, 20 meters is a wavelength. If this were 5 meters off the ground, 15 feet, it would have a pattern that is almost omnidirectional. If we get it up to one wavelength, see these nulls like we saw on the other one. We have 20 dB less signal going off the ends of it compared to front back broadside of that dipole antenna. So the height of it has a pretty drastic impact on the propagation pattern. This chart, this is called the azimuth chart. The elevation chart is the takeoff angle of the signal from the antenna. I've got a picture that illustrates the effect of this here coming up. But at one wavelength, notice that you have a low takeoff angle, and up to 25 degrees, you're just kind of blowing that signal from ground to the sky, which also has it has a big effect on a receiver that's within the near field close by. But if you're trying to work a long distance, having it up in the air with a lower takeoff angle is going to make a lot of difference. So I'm going to jump ahead to this one. This is the impact of takeoff angle of an antenna. This doesn't apply as much as a bunch of other propagation things that take place at VHF and UHF, different tropospheric ducting and whatnot. But in an HF signal, we're dependent on the ionosphere to reflect radio signals. So, one hop off of this station with a high takeoff angle goes up at a fairly high angle, comes back down. Multi-hop is definitely possible, but we're working closer stations to our transmitter, to our antenna. If we have a low takeoff angle, we hit the ionosphere at a much lower angle, and look where we drop. These stations probably wouldn't hear you, and you don't hear them. So obviously we can work much further. I'm not going to cover it now, but this is a decision factor that you may want to make in designing your antenna or your system to who am I trying to communicate with? If I want to work with everybody, you might make some compromises. If you're a DX sound and just want to work foreign countries, you're probably wanting a lower takeoff angle and a narrower beam width because I'm gonna point that antenna at a particular location. Yes?
So is there a way to know what, when you set that takeoff angle, how far that's going to propagate? Is there like a rule of thumb, or is there a chart you look at, or what?
There are calculators
Okay.
that where you can describe your antenna, and this will also be dependent on the height of the ionosphere, which isn't stable. So, yeah, there are, and that's another one of those, it just really depends on the conditions and what band, time of days, and all of those kinds of things. But in general, you can say one of the things is a vertical antenna has a lower takeoff angle. As we see, a dipole at least a wavelength above the ground has a relatively low takeoff angle. A compromised antenna close to the ground is going to have a higher takeoff angle and probably have a greater space, range of elevation. Yep.
I see on the previous diagram, 2 lobes.
No, these represent lobes at different heights.
So one wavelength above the ground.
Is this just this one? Half a wavelength is just this one.
There's 2 lobes.
Yeah, what's the base effect?
You do.
Yes, you do. Yeah. The multiple lobes, sometimes the ground actually is reflecting signal close to the antenna. So that when you raise it up and it's it's in certain ranges, it will give you multiple effects like that.
So you put your antenna out of one wavelength, does that mean close stations and far stations?
I don't think I'm prepared to answer that question. The answer is yes, but not on any real predictable manner. I mean, there's some goofy stuff that happens at this. You know, we talked about, well, we used to refer to this whole class as expletive magic. Because it's really, really hard to explain. So, you know, think about this as general concepts, and your mileage will vary. Even identical antennas at different locations will have different effects because we've got different resistivity in the ground, presence of other buildings that cause reflections and interactions with all of this stuff. So when you're thinking about putting up a new antenna system, don't overthink it. That would be my advice, because as I said, you can find ways to radiate off your rain gutters. Maybe not if it's on a steel roof, but that kind of defeats the purpose. But you can do some crazy stuff with some crazy designed antennas. So don't let it stop you. One of the best advice I've heard of people is don't invest too much money thinking that it's going to work a specific way, because you're going to find that it probably doesn't work exactly the way as advertised. But if you're prepared to realize that, or you have a pretty darn good antenna system if you start experimenting and doing different things. And the well-designed antennas, you buy a commercial tri-band Yankee. I don't know if they have the word bands or not, but anyway, if it's been commercially designed, it's been tested. And they can, the one thing that's kind of pretty neat about most of the ham manufacturers is that the reps are pretty friendly, and you can actually call them and ask them questions about, here's my situation, what do you think? And other hams, in a group like this, I'm thrilled to see so many faces that I don't know or haven't met yet. So there are people here that have a wealth of experience. Just ask questions. This community is pretty good about 98% of them are really good at, if not knowing the answer, pointing you to somebody that they know or has some experience with that. That's my advice. Another radiation pattern. Real quickly, don't want to spend too much. Near field, far field. Near field is the area inside of a perimeter where these rules about, we talked about for propagation, don't work. Close by, you're getting reflections off the ground, you're getting reflections off buildings, you're close by. Don't stand too close to a high ERP transmitter a radiator for very long. Far field, it starts now to take on those patterns that we've shown you. Far field is where the azimuth and elevation radiation patterns apply. Near field refers to the areas where propagation is interfered with. The other thing to remember, and this is again part of the magic of all of this, is that the power received is subject to an inverse square law, which means if I double the power, I square that number, and it's 4 times lower than it was when I got the antenna. So when you're thinking about the distance that we're receiving these and the level of power at those far areas, mind-boggling, magic. Cool. Now you know everything there is to know about antenna design. Steve?
Yeah.
Can you turn on the transmitter? Can't promise this is going to work we'll take it outside later on. We're going to see if we can demonstrate front to back ratio, or let's say talk front to back propagation and polarization. I'm receiving only. This didn't work real well when we tried it at 8 o'clock this morning. Oh. Full quieting. I don't know if you can hear it. It's a little. I'm not far enough away from it to get the real effect of this. I could just, as I pointed this away, I could just start to hear a little bit of the hiss. If we could back up and get closer to that threshold where we're full quieting and not, it's a lot more distinctive. But if you noticed, when I changed the polarization of this antenna, the antenna in the back of the room is horizontally polarized, and the signal diminished. It might have been more effective if I'd held it up here to show some directivity. But we'll demonstrate this a little bit, because it's pretty interesting how two elements like this can give you enough directivity to really notice that. The dummy load. Yeah, it's just it's a resistor, and it's vertically oriented. No, horizontally. I'm sorry, it's horizontally polarized. Yeah, there's a little more hiss off to the side. Oh. So, there's a good front to back in that particular case, if you notice. Some of that might have been, I'm blocking it too, and the body used to enhance. You ever do the old rabbit ears of the television and stand up